Hello and welcome to this video tutorial. My name is Stefan Müller, I'm a senior software engineer at IBV, and today we will work with our solution of a powerful and optimized EtherCAT Master Stack. This master software is optimized to run on small microcontrollers as well as on powerful industrial PCs. In this particular video we will work with an NXP i.MX RT1064. So I will show you how to run our master software on a evaluation board like this. Okay, so let's start. So first I will give you a quick overview of what we will do in this video. So first we will set up the IDE, then we will have a look at the icECAT EtherCAT Master Stack software package. We will install it to your system and build it on your system. Then we will build the master sample applications with the IDE. Then as the software part is done, we will bring the software to the target, in this case the i.MX RT1064 EVK evaluation board. We will run the sample application with the sample network. And last but not least, I will show you how to adapt the sample application to your own EtherCAT network. So here I have a list of the steps we will do. All the steps are marked as chapters in this video, so you can jump forward to chapters or skip chapters if you're not interested. Okay, so first we will talk about what you need for this video. Then we will set up the IDE. We will install the software package, building the software package, building the sample applications, running the sample applications, then a guide how to use your own EtherCAT network with the sample application. And then I will give you some hints where you can get some more information about our software products. What you need for this video is first of all the hardware. In this video we will use the i.MX RT1064 EVK evaluation board. We will build the project and run them on the MCUXpresso IDE in the version 11.3.0. So the projects provided with the sample package should also work on other versions of the IDE, but they're tested with this version. And to run the IDE with the processor, you need to install the SDK. This SDK can also be found on the NXP homepage, but you can find all the links in the description of this video. Okay, the next thing we need is our icECAT EtherCAT Master Stack software package, which is built of several modules. It's the master stack itself. Then we have the common package, which abstracts all the board and hardware and operating system. Then you have the optimized link layer driver, and we have the icECAT sample package. So if you have an evaluation package, all the three packages, the abstraction layer, the link layer driver, and the master stack, will be combined into one single package. And last but not least, we need an EtherCAT network to communicate with. The samples provided in the sample package work with a specific network, which is shown here. It's a combination of some digital out, digital in, and analog out, analog in modules. But as I told you before, you can also use your own network with the sample applications, and I will show you how to adapt the applications to your own network. Okay, so we start with setting up the IDE. So once you have installed the IDE, we simply open it, and it will ask for a workspace folder where you can store some settings and preferences and some metadata. So just select the workspace folder you want. Like I just created a new folder here on my desktop called workspace. You select it and click launch. And the first thing we need to do is install the SDK for the processor into the IDE. So you can download the SDK on the NXP homepage. In this case, we use the version 2.6.1 because the sample applications are based on this version. So down here you have the view installed SDKs. If you don't see this view, you can open it if you click on Window, Show View, and Install SDKs. Then you simply right-click in here, click on Import Archive. Then you navigate to the folder where you stored the SDK. The SDK comes as an archive file. Select it, open it, and the IDE will install the SDK. Now you're ready to work with the i.MX RT1064 processor. So now we will have a look at the software package. Okay, I copied all the packages we need in this folder. Up here we have the master package, then we have the abstraction layer package for hardware and operating system abstraction. Here we have the optimized link layer driver for this processor, and down here we have the sample application package. If you are working with an evaluation package, you simply have the sample package, and these packages are combined in one pre-built package. So all you have to do is extract all the packages to the same folder. Okay, to have a better overview, I will just delete the archives here. And here we have the content of all packages. So on the top level, you have some documents, which will also describe the steps we will do in this video, and some other documents you can have a look at. And up here we have the icECAT folder, which contains the master and the samples and all you need. There are some subfolders. There's some board support packages for which are needed by the sample applications. Then we have the common layer for the OS abstraction. Then we have the master stack itself. We have an install folder which works as output for all libraries and binaries we create. And down here we have the sample folder. Okay, and yeah, now you're ready to build this software package on your system. If you're working with an evaluation package, you don't need to perform this step, as the evaluation packages come with a runtime limited and pre-built master libraries. So you just can skip this step and continue with the next one. Okay, but we want to build the software package. For this, we need to first we need to ensure that the setting for the compiler is correct. So we navigate to the package path where we installed it, then to icECAT, common, build, make to, and then into the MK spec folder. Here we have a lot of files which contain all the configuration for the different supported target systems. As we're using this one here, the FreeRTOS 10 i.MX RT1064 EVK board, we can open up this, and there we have some variables set, like the operating system we use, the host system we use, and so on. And down here we can find the toolchain file. So this target system is configured to use the NXP MCUXpresso 1130, which is the one we installed. And we can find the configuration file for this toolchain down here. So there are some toolchain files for different versions. We are using this one here. This corresponds directly to the name we find here. So if you open up the toolchain file, we can find the toolchain path here, and this is set to the path where the IDE installs its compiler. So you need to ensure that this path is correct. If you're using the standard installation path of the IDE, it should be right here. So it should work with the default settings, which comes with the software package. Okay, so now we've ensured these settings are correct. We can go back to the top folder of our icECAT package and move to the icECAT folder, the master, then the build folder, the make2. And we will open a command line here. This can be simply done by typing cmd up here. We simply can type in make, and we get a list of all parameters we can use. The mandatory parameter is to the this one right up here, where we configure the target system we want to build for. There are some more values like the just build the debug build or release build or clean all, and some recommended parameters down here. So for example, do the parallel build. This will lead to a much faster build. But if you're using Windows and do the parallel build, it will kind of destroy the output of your compilation. So just for information, you can do the parallel build, but then the output is not usable anymore. Okay, so if we want to build our system, we simply need to type in make, and then we copy the target system up here, paste it down here, and press enter, and the compilation will start and build the whole software package. Okay, so I'll be right back when this process is finished. Okay, so now the build is finished and we have no errors, no warnings. We can close the command line here and have a look at the results of this build process. Okay, so we navigate again up to the icECAT folder, where we have all these subfolders. And now we can navigate into the install folder, which will now contain all the output of our build process. So in here we can find the following folders. Up here we have the include folder, which contains all the headers you need to use the EtherCAT master. So during the build process, all the headers are copied into the include folder. So this is the location where you find all the headers you need to include to use the master. The next folder we see here is the target system output folder. So in here we can find the debug and release folder, and in here the library folder. And here is the output of the build process we just did. And these are the libraries you need to link to your application to use the master stack. Okay, so now we can start with building our sample projects. Therefore, we open the MCUXpresso IDE, select the workspace. I use the one we created before. And once the IDE is ready, we can import the sample projects from the sample package. And this can be done by choosing the option import in the file menu, which you can find here, or simply click on the import projects link here in the project explorer. Okay, so here we can choose what we want to import. In this case, we want to import existing projects into the workspace. So we select this. And then we need to browse to the location where the sample projects are located. So we navigate to the installation path of our software package, where we can find the sample folder. Inside here we have the source code, which are these 4 folders here, and we have a build folder. And inside the build folder, we need to select the IDE we use. This is the NXP MCUX11. And in here we have different target systems. As we are using the i.MX RT1064 board with the FreeRTOS, we're choose this folder here. And yeah, now we can select the folder, and the IDE will show us all the projects which are located inside this folder. We don't need this test project down here. We just work with the sample projects which are selected now. And yeah, now we can click on finish, and the projects are now imported into the IDE. And yeah, so we have a quick look at the content. If we open up this project here, we see some linked source folders which contain the startup of the board, the operating system, and yeah, some low-level drivers from the SDK and stuff. And in the sample all folder, we have the main application code with the main.c, the entry point of the application. And down here we can see some memory configuration files, but we don't work with them in this tutorial. The last thing in this project we can see is the pre-built batch file, which is important because before we compile this project, we need to generate the source code from the network configuration file we get up here. So we will have a closer look on the last chapter, where I show you how to use the sample application with your own network. So just, yeah, watch this video to the end if you want to get some more information about this process. But what we need to do is execute the batch file, which will then convert the network configuration XML file we find up here into source code. We can do this by simply clicking a double click on this. We get the output. We can continue, and as soon as the workspace, the Project Explorer refreshes, yeah, it did it. We can see 2 more source files. It's the ENI configuration sample all.c and the header file, which now contains all the information of the network we are using. So you have information of all the slaves we use and the input-output variables. Yeah. Okay. So now that we have done this, we are ready to build the project. Before we build the project, we need to select if we want to build the debug or release binary. So this can be selected by right-click on the project, and the option build configuration set active, and here we can choose between debug or release. So in this case, we want to build the release build, which we can now see here. And to build the project, simply right-click on the project and click on build project. So now we'll get some build output down here. Yeah, and the build is done. At the end of the build, we will see some memory usage output. Yeah, as we can see here, it's quite big. This is not the master stack itself. This contains all the board support package, the sample board support package, which is included, some drivers for a terminal output and stuff, which is included, and also this application here includes the monitor application, which we will see later. So this is a combination of all. So this is the master stack itself is just a small part of this size here. Okay, now that we have built the sample all, we do the same on the sample simple. So first, yeah, it's the same content, like it's just another application here with this, yeah, some not that many source files and a little reduced functionality. But it's the same here. We have a network configuration file which we need to convert into a source before we build the project. So we execute the batch file down here. We get this output. And now we should see the generated files here. Yeah, they are here. Now we can select the build variant, but in this case, I'll leave it as the debug build. Then right click on the project and select build project. We get the build output down here. Okay. And now the sample projects are ready to run. So the output of the build can be found under the binaries tab here. So here's the simple application and the sample all application. Yeah, in the next step, we will talk about how to get these applications to run on your target with the sample network. Okay, so now we're ready to run our applications on our evaluation board. For this, you need to connect the evaluation board with an USB cable to your host PC. This will provide you an serial communication port, which you can use to see all the output the application gives to you. So yeah, and you can use any terminal application to open a connection to this serial port. I will use the TeraTerm. So we need to set the proper COM port. This done by serial port COM16. The settings for this serial connection are quite default. It's 115K with 8-bit, no parity, one stop bit. So we can open the connection and let's move the IDE here to the right. Okay, so first of all, we want to run the sample all application. So I connected the board to the host PC. And the second step, I need to connect the Ethernet port of the evaluation board to our network, which I've already done. And then we can choose the project we want to debug. In this case, it's the sample all up here. Just select it. And then you can go down here to the quick start menu. And there you have the option to debug your project. So just click on the debug. This will discover the debugger, which is located on your board. Press OK. And the IDE will start to upload the application to the board. Okay. So what we see here is that the debugger will stop the application inside the main function. So we're at the beginning of our sample application now. Up here you can find the default, the standard debugging controls. Yeah, and now if we just press F8, the program will start to run, and we should see some output here, and we should see some activity on our network. All right, so now we can see the output, like some statistics of the sample application and some transitions to from operational to init and so on. Yeah. Okay. So if you have problems with starting the application with the network and you need some more debug logging, we can simply increase the verbosity. We can do this by opening the source folder here, and in there we can find the application command line, which will give us the possibility to pass parameters to the application. In this case, we want to add a verbosity level and increase the level to this value. All the values you can find in the documentation and in the header files. This is just an example how we can get some more information out of the application. Okay, so now we've set this to a higher verbosity. We can simply build the project again. And move it to the right, and we will bring it back on the target. And when we start the program from the IDE, we will see some more detailed output here on the terminal. So yeah, this looks like a lot of information. So you can see like the names of the network which is used, and the serial number of the slaves, then the I/O variables that are configured, and so on and so on. Okay. So sometimes you have problems with stopping your application. So the debugger hangs up or something. There's the option of killing all active debug sessions. This can be done by this button. This sometimes helps a lot if you need to clean up some debug sessions that are still running in the background. Okay. So yeah, now you're ready to run your application on the target. You're ready to debug the application on your target. You can increase or decrease or select the log level you want. There's one more option I want to show you. Now the application is linked into the flash of the target. We can also link the application to the RAM, which will increase the execution speed. This can be simply done by changing the properties of the project. But take care, if you change the properties of the project, ensure you remove the write protection from the project file. If you do not do this, this can lead to problems within the configuration of your project. So first remove all the write protections, then modify the project settings. Okay, so link the application to the RAM can be done by right-clicking here, enter the properties. Then we go to the C build, then the settings tab down here. Then we select the under the MCU linker, we can find the manage linker script. And there we have the possibility to link the application to run. Okay, so we just need to check this option, apply it, and we close the properties. Now we need to rebuild the project. And now we should see, yeah, there's no more usage of the program flash. So all the application code is now in the RAM of the target. Okay, and if you want to run this, it's the same. Just just select the project you want to run. Click on the debug button, and then it will take some time, and the binary is transferred to the target. And here we are. Okay, now we come to the last step of this tutorial, which might be the most interesting for you. In this step, I will show you how to use your own network with the sample application. But before we dive into the practical thing, I want to show you how the whole process of integrating a new network into the sample application works. So first of all, you have your own EtherCAT network. Then you need a tool like the configuration tool from Beckhoff. It is called a TwinCAT. And with this tool, you can configure or scan your network. And then you get all the information about all the slaves you have in your network. After that, you can configure your network like you want, like renaming the input outputs or configuring your slaves. And after that, you can export all this information into an ENI file. This is the file we already seen in the sample application. And this was the file we converted into source code. And this file contains all the information of your network. And this looks, for example, like this. So here we have some input channels, which are called button 1 and button 2. And down here we have a switch and another switch. And yeah, all this can be done by using a tool like TwinCAT. But we also have our own solution for generating these any configuration file, and this is called the EtherCAT configuration library. If you want information about this, you just can contact us. Okay. So now that we have our XML file, we will go to the sample application. First of all, we will adapt the sample application so that we remove all the network-dependent source code. Then we will convert the XML ENI configuration file into source code. This is the same process we've done before in with the sample all and sample simple application. This generated header will look like this. Here you can see the button 1, button 2, switch 1, switch 2 inputs we've seen before in the ENI file. And then we will implement a small application where we read some inputs and write some outputs. And after that, we will compile the application and link the application to the master libraries. And this will result in our master application. Okay, then we will bring the application to our target and connect the target with the network, and then we can communicate with slaves. So here we are back in the IDE. We have our sample applications open, and yeah, for this step we will work with the sample all application, which is prepared to use it with your own network. Okay, so first of all, we need to bring your own ENI network configuration to the project. So the ENI configuration of the sample project is located in the sample all folder in the ENI folder here. Okay, so I made my own configuration, which I have here on the desktop. This is just it's the same ENI configuration as we used in the sample all, but I renamed 2 variables. We will see this later. Okay, so I simply copy this file and bring it into my ENI folder by pasting it here. So the simplest way is to just rename this as this. So we can use the batch script down here to convert it to source code. Okay, so I simply remove the old XML we don't need anymore, and we rename this to icm sample all.xml. Okay, so the next thing we do, we delete the old generated source files here, and then we can generate the new source files from your network, or in this case my network, by just executing the pre-built script here. Okay, so now we should see the source files here, and as I mentioned, I took the original standard source as standard configuration and just renamed variables. So let's have a look where we can find it. I renamed it to analog in, analog out. There we have it. So this is a name I gave. It's the analog input channel 1. And then we should find an analog output. Yeah, located here. And we should also find a variable called alarm, which is just a simple output, and we can find it here. All right, okay, so this worked. The next thing we need to do is remove all the network dependent source code which is included in the sample. All the source code is located in the sample.c file here. We can simply rename the sample file to something like sample like this. So if we rename it like this, it's just excluded from the build. And in the project, we can find a source file which is called sample.c template. And if we rename this to .c, we included the file to the build process. And this file is a complete empty application. You can find some comment inside here where you have to, for example, read your inputs or write your outputs. Okay, so now all the network dependent code, which was all the sample application code, which provided information to the network or read some variables of the network, is now removed from the project. Now we have a clean project which doesn't do any processing on the network dependent variables. and input outputs. And now we should be able to build the project. So just right click on build project, and there we go. Perfect. Okay. So now I will show you a simple program where we read an input and write an output and do some little logic in between. To do so, first thing we need to do is include the generated header file. This is the ENI config sample all, because all of the IO definitions we want to use are located inside the header. The next thing we will do is we will read an analog input. So first of all, we need a variable here in the code for the analog input value. This is the, let's call this value. Okay. Then we can use the access macros to access the IO variable. This is called EtherCAT. This is an input, so ivar. And we have some options here, and the value we want to read is a 16-bit value, so we use this. We have to pass the cyclic context, which is passed to the cyclic application here, the cyclic process here. Then we need to pass the name of the variable we want to read. And this was the one I showed you before. It was the analog input channel 1. Yeah, this was the value we've seen in the header file. And then we need to pass a reference to the variable we want to write the value in. Okay. So with this line, we read the current value of the analog input channel 1 of our network. Okay, so the next thing we need is an alarm. So let's create an alarm variable up here. Initialize with 0. Okay. And what we want to do is, depending on the input we have here, we want to set the alarm or clear the alarm. So here we have the common process data in here. So I come down here and let's say if our value is greater than 10,000, for example, we will set the alarm to 1. And the next thing we need to do is write back the alarm to the process image of the EtherCAT frame, so that it will be transported to the slave with the next frame. This can also be done with the macro like we see up here. So we can type in now we have an output variable, and we want to write 1 bit. So no, this is wrong. We want to write 1 bit. We need the cyclic context. We need the the name of the variable we want to write. This is the ini output variable alarm. Yeah, this one. And we write the value of alarm to it. Okay. So now we have this simple application in the cyclic process, which is called every millisecond, for example, in this sample application. And this will read the value of this variable, which can be found in the header. And if this value is greater than 10,000, it will set the alarm, and then the alarm variable will be written to the output of the, which is called alarm, which is a simple digital output. So if we put this on our network, we can control the analog input here with the analog output, which is also in the network, because if you write a value to the output is bridged to the analog input. So the output we write will be the same value that the input will read. And so we can manipulate this value here. And if we push it up to be bigger than 10,000, we should see a digital I/O pin to switch on or off. But before we start the sample application, we configure one last thing. Therefore, we open the application command line file in the source folder. And what we want to do is first we want to disable all the logging, and we want to enable the monitor application. This is a terminal application, which you will see in a few seconds, with which you can control the network and get access to all the I/O variables of the network and the network state and so on and so on. Okay. Furthermore, if you want, there's an example command line provided up here. You can also change the cyclic time of the processing we just did. So the cyclic process time is configured by default to 1000 microseconds, so 1 millisecond. But you can run your sample application with, for example, like a value of 500 microseconds or so on. Yeah. Okay. So now all the modifications in the source code are done, and we can build the project. And okay, let's change the configuration to debug so that we can stop the application if we want and see some and step through it. So let's build this as debug. Okay, so now my target is connected. Disconnected to my host PC with a USB cable and disconnected to my network. Now I will open again the serial connection to COM16, and I will move the IDE to the right. And now I select the sample application and click on debug. Okay, the application is now transferred to the target, and now we're in the main function at the start, and if we press F8, the application will run, and here we can see the monitor application. This monitor tool is used to control and get an overview over the network you have. So, for example, if I press Shift N for network, we come to this network view, and there we can see the network we have, and these are the slaves we have in this network, and here we have the state of the network. If I press the S to change the state, I can set the network to the different states, which we can see down here. For example, to init, and all the slaves and the master will go to the init state. And if we want, we can bring it back to operational by pressing O. Okay, and our network is operational again and is running. There are a few more windows we can see, and for example, if we press Shift R, we can see all the slave registers here, and if I press F5, we get an update, and the master will read out all the values of the slave registers, and we can see the content here. Okay, if we press Shift I, we have the I/O variables. So this is where we want to modify the analog value. So if I go down here, this is the analog output, which is bridged to the analog input up here. So if I enter a value like, let's say 200, no, okay, 200, and we have 200 here, and it is physically bridged to the analog input, which is up here. So 200, 200, okay. If I scroll down here, we will see our alarm variable, which we have here. So if I increase this value to over 10,000, this value should become 1. So let's try this, and simultaneously we can have a look at the network. If I increase the value over 10,000, the alarm LED will turn on. Okay, so change this value to like 11,000, and if I hit enter, we should get the 1 here. Okay, so now we have an active alarm. Okay, perfect. So now you're able to write your own master application, and you can process the data of your own network, read the inputs, process the data, write the outputs, and do whatever you want to do with the network. Also, you have the possibility to control your network and monitor your network with the icECAT monitor application. We just did a brief overview of what you can do with the icECAT monitor. You can find a lot more detailed view on this application inside the icECAT software package, where you can find a lot of documentation files and reference manuals, and to all the stuff we did in this video. Okay, all the documentation I talked about is located inside the EtherCAT software package. So if you open up the icECAT folder where we installed the software package, we can find some PDFs here, which contain the programmers, for example, the programmer's guide for the optimized link layer driver, the licensing models, the release notes, and more documentation can be found in the icECAT master package and the common package. So if we navigate here to the master, we can find a folder named _doc, which contains the monitor user guide which describes the monitor application we saw. Then we have the integration guide for this board. This is all the things we did in this video described in a document. And down here we have the programmer's guide, which describes all you need to do to get your own application running, and how you can integrate the master into your software environment. And yeah, last but not least, we have the reference manual where you can get all the documentation about the master API and all the functionality the master gives to you. Okay, so now we're at the end of this video tutorial. If you want more information on the icECAT product, you can simply go to our homepage or contact our icECAT team. We also offer Helpdesk support. For this, simply contact our Helpdesk team via email. All these email address and the homepage address will be also posted in the description of this video. Okay, thank you for your time. I hope I could guide you through the first steps with our master stack on the i.MX RT1064, and I hope to see you in the next video.